For this FRQ, we're talking about a screensaver on a computer screen with two circles that start as dots and expand outward. A particularly exciting real-world example here for today. So at the instant, the first circle has a radius of 9 centimeters. The radius is increasing at a rate of 3/2 centimeters per second. And we want to know the rate at which the area of the circle is changing at that instant, and we need to include units. So whenever we have time here, centimeters per second, changing at that instant, this is related rates. So we'll start with the area of a circle. Area equals pi r squared, and we will differentiate with respect to time all the way across. dA dt equals 2 pi r dr dt. And we know that, let's see, rate of change of the area, that's what we're trying to find. Radius is 9. dr dt is 3/2. So then dA dt will be 2 pi times 9 times 3/2. So dA dt equals, I'll leave the pi for now, 2 times 9 is 18, divided by 2 is 9, times 3 is 27 pi. So we end up with 27 pi. Rate of change of the area will be centimeters squared per second. For part B, we have a model for the radius of the circle. So at any given time between 0 and 6 seconds, this will tell you the measure of the radius. And we want to know at what time is the radius of the circle increasing at a rate of 3 centimeters per second. So basically we're looking at the rate of change of the radius. So if this is the radius, the rate of change of the radius is going to be w prime of t, or dw dt. It's no different than thinking of dy dx and f prime of x, same sort of thing. So the derivative of w, derivative of 12 is 0. Derivative of negative 12 e to the negative 0.5 t is itself negative 12 e to the negative 0.5 t times the derivative of negative 0.5 t, which is negative 0.5. So we end up with w prime of t equals negative 12 times negative 0.5, which is 6 e to the negative 0.5 t. And then we were looking for when the radius was increasing at a rate of 3 centimeters per second. So we're looking for when w prime of t was 3. So if 3 equals 6 e to the negative 0.5 t, we just need to solve for t. Divide by 6 on both sides, we get 1/2 equals e to the negative 0.5 t. To get t out of that exponent, to get rid of the e really, we'll take the natural log of both sides. So on the left side we have natural log of 1 minus natural log of 2. On the right side, natural log and e cancel. So the natural log of e is 1, so we get negative 0.5 t. Natural log of 1 is 0, so if we divide by negative 0.5, t ends up being natural log of 2 over 0.5, because these negatives will cancel. This is the same as natural log of 2 divided by 1/2, and since dividing by 1/2 is the same as multiplying by 2, we end up with t equals 2 natural log of 2 seconds. Part C. Now we have a model for the radius of the second circle. We have f of t measured in centimeters, t is measured in seconds, just like the rest of it. Now what we have is the rate of change of the radius of the second circle. So essentially to find how many centimeters the radius increases from 0 to 3, we're kind of looking for the accumulation here. So we can do the integral of f prime and that will give us f of t. So the integral of t squared minus 4t plus 4 dt from 0 to 3. And this is equal to t cubed over 3 minus 4t squared over 2, which is 2t squared, plus 4t from 0 to 3. This is equal to, well, 3 cubed is 27 over 3 is 9, minus 2 times 3 squared, or 2 times 9, which is 18, plus 4 times 3, which is 12, minus, well, you put 0 in any of these, you get nothing. So that's just 0. So we end up with 9 minus 18, which is negative 9, plus 12 is 3. So we end up with 3 centimeters of increase from t equals 0 to t equals 3.